Given that today is a good old-fashioned algebra day, what's going to be very important is for us to remember a lot of the algebra rules that have developed with these two functions. So you see that orange piece of paper you have? It has all of the rules for exponents, which was Unit 2, Part 1. And it has all the rules for logarithms that we learned in the last few days. It also has the shapes and things like that to help you condense your studying down later. But the main thing is we're going to be looking for those properties of exponents, properties of logarithms, to be able to use them to solve equations. Now we are going to be solving equations, which means we're going to be working on isolating and working with inverse operations, among other things. But today we're going to be solving both exponential equations and logarithmic equations. There's two sets of ways that the exponential equations can occur. Our entire front page is exponentials, so not logarithms, exponentials. The first way that you can solve an exponential is when the bases that you are using are in the same power family, meaning you can rewrite the equation to where it would be like 5 to the third power equal 5 to the x power. If the bases are the same, then we can use the one-to-one property of exponentials to just basically get rid of the bases and work with the exponents only and solve. So for example, this example number 1a is going to be like this. The reason is, do you notice that 16 is in the same power family as 2? 16 is 2 to what power? The fourth power. So if we just rewrote this as, can we rewrite? 2 to the 3x minus 16 equal to 2 to the fourth power, because you guys just told me that 16 was 2 to the fourth power. Do you see now that the bases match? If the bases match, all we have to do is take the exponents and set them equal to each other. This is a one-to-one property of exponentials. Since it passes the vertical and horizontal line test, it would have an inverse. We can do this. And then we just solve like normal. What would we do on both sides? Add 8. What would we do then? Divide by 3. The solution here is 4. The end. How do we feel about that? Okay. Let's see if we can do it again, but I'm going to make it a little harder because sometimes the bases shown on your paper are not the base power family you're using. Do you recognize that 27 and 9 are not in the same power family if you think about the bases of 27 and the base of 9? But they are in the same power family when you switch the base to a certain number. What number? I think I heard somebody say it. 3. 27 is 3 to what power? 3 to the third power is 27. So this would be like 3 to the third power, still multiplied by that power that was originally there. How could I rewrite the base of 9? 3 to the second power. Now that the bases are the same, notice I left the extra stuff there, right? Now that the bases are the same, we just take the exponents and set the exponents equal to each other, because if those bases are equal to each other, then that means the exponents also have to be equal to each other. For this particular one, it does require us to distribute, and then we will combine our like terms, inverse operations, all that good stuff. So we distribute, this becomes 3x plus 9 equal to 2x minus 2. We would subtract 2x from both sides. So minus 2x, that ends up with x. And what's my very last step here to solve for x? Minus 9 on both sides, which means x is equal to negative 11. How do we feel about that? Questions, comments, concerns? Pretty easy, right? This is why I was being so annoying about those flashcards, because if we recognize things being in the same power family, we will know that we can use this easy method to solve. If perhaps you recognize that numbers like 4 and 15 are not in the same power family, because, right, 4 to the second power is 16, so it's already too big. We're going to need the second set of instructions. So if we look at the top of our paper right here, it says when the bases are not in the same power family, you're going to isolate the base and the power, the exponential expression. You will take the natural logarithm on both sides. So similarly to when we added on both sides or divided by on both sides, you're going to put natural log on both sides. Then you're going to simplify using the properties of logarithms from lesson 2.12 that is also on that formula chart that I gave you. Most notably, it's probably going to be the one where we take the exponent, bloop, and we drop it into the front. Yes? After that, you'll finish solving for the variable with regular inverse operations and round appropriately. So for example, again, we notice 4 to the x equal to 15. 4 and 15 are not in the same power family. The base and the power is isolated though. 4 is isolated. So what we're going to do is we're going to put natural log on both sides. So natural log of 4 to the x equal to natural log of 15. We're putting natural log on both sides. We are taking the natural log of both sides. Do you remember, and if you don't, look at the orange formula chart. The property is called the power property of logarithms. What happens with this exponent? Where does it go? To the front. So we're going to take this little x right here and we're going to go bloop, drop it in the front. So this becomes x times the natural log of 4 equal to natural log of 15. If you're immediately about to ask me why I switched from cursive to print, there's no good reason for that. It's ln. And sometimes if I write in print, everybody thinks it's in. It is ln, natural log. And I will accidentally go back and forth between the two handwritings. I'm sorry. Okay, but now that we have the x in the front, remember our goal was to get the x by itself. What is currently next to this x that I want to have go away? The natural log of 4, right? How do I get rid of this natural log of 4? So currently it says x natural log of 4. When two things are smushed next to each other like that, what are we doing with them? So how do we get rid of it? Dividing. We're going to divide both sides by natural log of 4. And if we divide both sides by natural log of 4, those are going to cancel out. So then all we have left is x being equal to natural log of 15 divided by natural log of 4. To make sure that we understand this, because this question could show up on the calculator or non-calculator section of the test. If we're on the non-calculator portion of the test, we're done, because this is called an exact answer. If we are on the calculator portion of the exam, you're going to have to put that into your calculator. So with your calculators right now, I want a decimal approximation to how many decimal places? 4. So you do the fancy fraction. There's a button for natural log. Do you remember where it is? So then 15, close parentheses, go to the denominator, natural log button again, 4, close parentheses, and then enter. Then round that number to 4 decimal places.
Wait, how do I
Nice, yeah, 1.9534. That is the decimal approximation. I'm just going to write down rounded because decimal approximation is a lot of letters to write down. But again, make sure you know the difference because there will be both that are asked for, whether that's the decimal approximation or the exact answer.
I don't know what I do. I got 2.38.
Okay, I'll come help you. What's your question? Go ahead. Now let me make it where we have a few beginning steps that we've been avoiding so far. Letter D is actually a pretty easy question, but the problem is the base and the power are not isolated. Right now, I want us to recognize what the base of this expression is. What is the thing with a power? E, not 40E, E. So for us to be able to solve this, we need to get the e to the 0.6x by itself. Essentially what we're doing is we are pretending, I'm gonna use a different letter. What letter should I use? Not X or Y? G. Great. We're pretending we're trying to get this G by itself. We're like substituting in the concept of e to the 0.6x to solve for G. What are the two steps I would do to solve for G here? Add 3 and divide by 40, correct? So we're going to do that, but we're going to do that to this function. Leave your G there. Leave your G there. I know I just erased it and you're all panicking. Leave your G there because that is what we're solving for. So just like you guys told me, we are going to add 3 to the other side. Yours would say 40. Yours would say 40G. Okay. And then how do you get the G by itself? Divide by 40. So if I divide by 40, I have not substituted G in for mine. but I can still do so. The reason I had you put a G there is because a lot of students struggle with the concept of isolating a particular value when it's not just a cute little X or one particular number. So you doing this with G's right there is exactly what I'm doing on the board without the G being there. Do you see the difference? Yeah, I did 240 divided by 40, and I got 6. It is typically you use the letter U, and it's called U substitution, and yes, you are. I would prefer us to not need to do that, which is why I didn't write it on my notes. But if you need to isolate a particular letter when you're working on the isolate the base step, that's totally fine. Just make sure you put the correct base and power back. Because now that I have e to the 0.6x by itself, we notice that e and 6 are not in the same power family, so we take the natural log of both sides. ln of e to the 0.6x equal to the natural log of 6. Does anybody have any spidey senses going off here? Say again? Like, boop, drop it in front? Is that, what do you mean? Okay, when we did this dividing step, this is what you're talking about right here. We can't do that until the x is out of the exponent.
Oh, so you would just bring the x in the front.
Correct, yeah. Now that we've taken the natural log of both sides, we can take this exponent and move it to the front. And that's why we take the natural log of both sides. We want to use this property to properly solve the equation. So this would be 0.6x times the natural log of e equal to natural log of 6. Y'all, for real, nobody has any spidey senses going off about natural log of e?
No.
Don't write this down, just look. Natural log of e, isn't that a log with a base of e?
Yeah.
Should it be the same?
Yeah, what happens when they're the same?
They cancel out.
They cancel out, so we really could just get rid of this natural log of e part.
Wait.
Because you guys, we recognized this before where you had log base 7 of 7 to the x, that cancels out, right? You can do the same thing if the base is e. If you don't notice and you just keep solving with that log of natural log of e, you'd be fine. But let's use our spidey senses here. So Layla, what should we do now that you wanted to do earlier? Very good. So we're going to do natural log of 6 over 0.6. That is your exact answer. And then if we wanted a decimal approximation, we'd go to our calculator, use the fancy fraction, natural log of 6 divided by 0.6. Go for it. Let's make sure our fingers remember how to do that. I agree. There's our decimal approximation. So really the only choices you have to make for yourself is if you're using the first method or the second method to solve. If they're in the same power family or you need to use natural logs. Yes?
Do you do that weird equation sign?
Oh, the little squiggly lines? Great question. Do you have to do the squiggly lines? No. I do it because as a mathematician, I like to know I rounded that number. And so that symbol to me tells me that that's not an exact answer, but that it's rounded. It is not required. It's nice flair, but it's not required. There are also just two cases really when it comes to logarithmic equations. The first one is when there is logarithms only on one side of the equal sign. If there's only logarithms on one side, you will condense the logarithms to a single logarithm using properties of logarithms. I said the word logarithm like 8 times just now. Then once it is isolated with the log by itself, you will use the log loop, which again is printed on your orange piece of paper, to rewrite the function into its equivalent exponential form. When you do that, the x will now be able to be solved for using inverse operations. The only important thing here, and we're going to circle number 4, not with a highlighter, Miss Quigley, but with a regular piece we're going to circle number 4, we're going to put a little arrow right here, and we're going to put a bunch of exclamation points. Because this is not just like, you should check your work, teacher talk. The type of function we are solving is a logarithmic equation. There are domain restrictions for this function type. So we may solve the equation correctly and still have to throw away our answer. We have to check for extraneous solutions. Sound good? Look at number 1. How many logarithms do you see there? 1. It's all on one side. That means we're using this first method. When we condense to a single logarithm, we're already there. We're going to use the log loop. What is the base of this logarithm? 4. What should be the new power if we're doing the log loop?
X equals 3.
The inputs and the outputs have to switch if we're doing inverses. 2, and that's going to be equal to x plus 3. This is just straight up the log loop. 4 times 4 is 16, so this is 16 equal to x plus 3. We subtract 3 from both sides. We get that x is equal to 13. Now, before we box this answer and call it a day, we have to go back and think about the extraneous solutions. All we're going to do is take this answer and mentally, because you can do this in your head, plug it into the inside. If I put 13 right here, what number would I get inside?
16.
Is that a positive number?
Yes.
We're good to go. We checked our work. The answer is 13. As long as what you get is a positive number, you keep your answer. Sound okay? Let's try another one. This time, are there logarithms on one side or both sides?
So one side.
One side. Is it isolated?
No.
No, there is a 3 in front of that natural log. How do I get that 3 in front of the natural log to go away?
Oh, would you move the x to the front?
That's only if it was an exponent. Good idea. That's only if it's an exponent. This is not an exponent. I just want to get this 3 to go away.
You divide?
I divide because 3 natural log means 3 times natural log. So I get rid of the 3 by dividing. This becomes natural log of 2x equal to 4.
I thought you can only divide after adding or subtracting.
Correct if we're PEMDASing, but this stuff, the natural log of 2x, is what we're isolating. We're pretending like we're trying to solve to where it says natural log equals, which is what we did. If there was some adding and subtracting behind that natural log, we would have done that first, yes. Okay, 1 natural log. It is isolated. We go for the log loop. What is the base of this logarithm?
4.
I've heard, no, those are, 10 is a okay answer, but it's not 10. That's regular log. Natural log is base E. Guys, you had this one earlier. We knew this. What happened? This is base E, so I'm going to rewrite this as E to what power? 4 equal to, so whatever was inside has to go on the other side of the equal sign now, because it has to switch inputs and outputs. We got to get better with our log loop. That's okay. We'll work on it. Okay, remember, we're trying to get the x by itself. What do I have to do to get the x by itself? Divide by 2. So if I divide both sides by 2, I have e to the 4th power divided by 2 equal to x. We're back to having an exact answer and something that we can round and get a decimal approximation. Here's a fun question for you. How do you put the e in the calculator? Second ln or second divide. You get 2 options there. So you do second ln or second divide to the 4th power divided by 2. We should get approximately 27.299. Should round up to 1. There's our rounded or decimal approximation answer. Okay, cool. We try another. How many logarithms do you see here? 2. Are they on the same side or opposite sides?
Same side.
Same side. So we're still using the same rules. It told me that I'm going to need to combine them using the properties of logarithms. The property of logarithms that we learned about before told me that if I'm adding these logarithms together, what do I do with their insides? Multiply. If you're like, where are you getting these rules from? It's from your reference sheet that I gave you. The product property of logarithms says if we are adding logarithms together, we can multiply. Multiply, add, divide, subtract, power to the power, multiply. So we can rewrite this as log base 2 of x times x plus 7 equal to 3. Now that's a lot of parentheses for no good reason. Can we go ahead and distribute that x in there? What's x times x?
X squared.
And then x times 7? 7x. So you really could write this as log base 2 of x squared plus 7x equal to 3. You could also do all of that in one step if you know how to distribute very confidently. Okay, the base is 2. The logarithm is isolated. We can go ahead and do that log loop. This is going to become 2 raised to the third power equal to x squared plus 7x. The base raised to the output equal to the input. We've switched them. 2 to the third power, what is that? 8. So really this is saying 8 equal to x squared plus 7x. Our goal after we get rid of the exponents and the logs is to solve whatever type of equation shows up. What kind of function is it when there's an x squared? Quadratic. How do we solve a quadratic?
You're gonna have to do the. I forgot what's called. You do.
Factoring?
Yeah, that.
You're going to make a little X puzzle for me. But to do that, these kinds of equations need to be set equal to 0. So we subtract the 8 from both sides. We get x squared plus 7x minus 8. We're thinking of numbers that would multiply to make negative 8 and add to make 7. 8 and negative 1. So we'll do x plus 8 as one factor and x minus 1 as the other factor. Once we have it in factored form, we just switch the signs to get the solutions, which means we think the solutions are x equal to negative 8 and x equal to 1. Before you box this answer, we check them. Because the answers you get when you have a logarithm from the start needs to be checked each and every time. So if we take this number negative 8 and we put it inside this logarithm, is it a positive number?
No.
No. Throw it away. We check the second one. If we take the number 1 and we plug it in this logarithm, is it good?
Yes.
If we plug it in this logarithm, is it good? Yeah, 1 plus 7 is 8. That's a positive number. So we only have one solution here. This is why you have to check. We would have answered with 2 solutions unless you check your work.
So it can't be negative numbers at all?
It can. Don't think any negative number you get, you throw away. It has to be the logarithm's argument, meaning the stuff inside the logarithm, has to be positive. So if you plug this in, like maybe it didn't have this one and it was only this, and you get the number negative 3 as an answer, what's negative 3 plus 7?
4.
So it's okay. That's still a positive number, as long as the inside is a positive number when you plug it in.
Okay.
Let's try one more. What do you notice about this one?
It's natural log on this, well,
And there's a fraction.
on the same side.
We see there's a fraction. Are there logs on both sides? Ooh, now we have a second set of rules. It's actually easier. It says condense the equation on each side into the form isolated logarithm, using properties of logs. Then you're going to use the one-to-one property of logs to basically get rid of the logs themselves and just set the insides equal to each other. Then you solve for the variable and you check your work. So again, maybe hit up this number 4 with some arrows and some exclamation points, because even though this is the different case for logarithms, same vibe, we always have to check our work with logs. So let's see what this one might look like when we solve using these steps. Again, it tells me to condense them on both sides. So when I'm subtracting these two logarithms, what do I do with their insides? Look at your orange sheet. When I was subtracting logarithms, I can't hear you, I'm sorry. Divide is correct. So that means on the left side of this equal sign, your logarithms will condense down to 1 by putting x plus 2 in the top and 4x plus 3 in the bottom. And now I have isolated log equal to isolated log. Do you see that? Drop the logs. They're gone. There's a one-to-one property for this function type, which means that we can just take the insides and set them equal to each other. At this point, you just solve whatever type of equation showed up. The type of equation that showed up for us is a proportion. How do we solve proportions? It's everybody's favorite thing from like middle school math.
No, it's not. Butterfly.
Ah, isn't it your favorite thing though? Your faces light up whenever we get a proportion. So I don't know, you might be lying to yourself. You guys love proportions. 1 times 4x plus 3 is 4x plus 3. X plus 2 times x. I'm going to write that one down so we can show our work because it's going to require us to actually do some math. This is going to become x squared and 2x.
So can I drag the 4x plus 3 down equals x squared plus 2x?
Agreed, yes. Now, what kind of function has appeared? Quadratic. What do we do with quadratics? Factor. So we set them equal to 0 and factor. This time, that means I'm going to move two pieces. If I take the 4x and I subtract it to the other side, 2x minus 4x is negative 2x. And then I'm going to move the positive 3 to the other side, so now it's negative 3. What numbers multiply to negative 3 and add to negative 2? Negative 3, positive 1. Which means that my solutions, my proposed solutions, are 3 and negative 1.
Wait, did you flip them once you get the answer?
Correct. From factors to solutions, they're opposite signs.
X plus 3, 5.
It comes from setting the two properties equal to 0 and solving. Can I box both of these answers? No, because we started with logarithms. We have to check. If we plug 3 into the first one, 3 plus 2, is that a positive number?
Yes.
4 times 3 plus 3, is that a positive number? 1 over 3, is that a positive number? Okay, so 3 is good to go. Now we try negative 1. Negative 1 plus 2, is that a positive number?
Yes.
Okay, seems pretty good. 4 times negative 1 plus 3.
No.
4 times negative 1 is negative 4. Negative 4 plus 3. Ah, that's negative. So get rid of it. The moment it doesn't work, throw it away. There's only one solution here, again. Make sense? Okay, last but not least, let's see how we can help ourselves out here. There is a way to solve these sorts of problems on the calculator. For this problem in a calculator required context, what we're going to do is we're going to let the first function be what we type into y1, and the second function, g of x, be what we type into y2, because it wants to know all of the values of x where the graphs intersect. The graphs intersecting means that we're trying to find where these two equations are equal. But intersecting means that we're just going to run the intersection program on our calculator. So we're going to let y1, when we type it in our calculator, be the entire function f of x, and y2 be the entire g of x function that is on our paper. I'll give you a pause to type. Go ahead and press y equals on your calculator and type these in. You're going to be looking for the intersection point. If you've forgotten how to find the intersection point, once you can see it on your graph, I'm going to write it on my paper just so you can look up and see it. we should get that the coordinate point where they're intersecting there is the coordinate point 2.3166, comma, 1.67, LOL, 08. Okay, now when we're answering these questions, make sure you know what the question is asking for. This one does ask for the values of x. So we're answering with the first coordinate point. There is a time where you might be asked for the output value where they intersect. So just make sure you read the question to know if they're asking for the input or the output value. Now, every single one of the questions we've done can be solved this way. So if you're on the calculator portion of your exam and you don't need an exact answer, you just need a decimal approximation, you can solve every single one of these that we did up above this or even on the other page by making this side y1 and this side y2. y1, y2, y1, y2, y1, y2. Same vibe. But of course, we have non-calculator portions of the test, and I am going to be asking for exact answers, which means we can't use the calculator.
What's the